This video, we're going to go over graphing square roots and some methods that we can use to be able to graph those particular functions. Before we get into those rules, we're going to first look at what does the square root function look like. And to do this, we're going to make a table and we're going to use the following points here. We're going to plug in 0 to the square root of x, and the square root of 0 is 0. Next we move to 1. The square root of 1, 1. Plug in 4. The square root of 4 gives us 2. And the next number, square root of 9, is 3. And these create ordered pairs. So we go over to our graph, and we can plot a point at 0, 0. Next one at 1, 1. At 4, 2. And the last one here, we're going to do 9, 3. What's special about this graph is that this is not a two-way arrow. It starts at 0, 0. The dots that we were plotting were working in the direction to the right, so we can draw a one-way arrow going to the right. And next thing is what would be the domain and the range of this function here. Well, first let's look at domain, the x values. If a number is part of the domain, then if you look at the x-axis, there should be a dot either above the x-axis, below it, or on the x-axis. If you go from the negative side and you work your way to the right, the first number that you're running into would be 0 on the x-axis. And then everything to the right of that is always bigger than 0. So our domain here, it's going to be the x values that are greater than or equal to 0. Another way to look at the domain is, look at the x values in our table. The smallest number is 0, and 1, 4, and 9 are all bigger than 0. Now let's look at the range. Same idea. Do I have a dot to the left? Do I have a dot to the right? Or, and do I have a dot on the y-axis? When you work from the negative direction up towards the positive direction, the first number you run into is 0, and all those dots are above 0 on the y-axis. So its range are the f of x values, sometimes you could say y, is greater than or equal to 0. Again, look at your table. All the y values in that table, or the f of x values, are bigger than 0, or they're 0 itself. So this is what we call the parent function, and that parent function could be shifted right, left, up or down, and it could be reflected. It could have a number of things happen to it. And what that leads us into is what we call a transformation form. Transformation form has a lot of really nice properties with it because these rules apply to all functions. And the three rules that we're going to look at are A, H, and K. I'm going to start off with the H number because H stands for horizontal. You're going to see one of two things. If it says x minus h, the number that's there for the h tells you how much this graph is going to move to the right. If it says x plus h, this tells you how much the graph is going to move to the left. Jumping out to the k value. K stands for vertical. And if you see plus k, that tells you how much to move all of your dots from your parent graph up. If it says minus k, we move all the dots from the parent graph down k times. The last rule that we're going to look at is A, standing for amplitude. A few things to look at here. Is A less than 0? Or in other words, is A negative? What this does is it reflects over the x-axis. So our graph that typically was going up to the right is now going to go down to the right. The next thing, I don't care whether the number is positive or if it's negative, as long as its value, if we were to do the absolute value of it, is greater than 1, this is going to stretch the graph vertically by a factor of A, meaning that we're going to be multiplying some numbers by that number. And the last thing to look at, if that fraction, or maybe the decimal, is between 0 and 1, then instead of stretching it, we're going to be compressing it. This graph is going to be pretty flat, as opposed to stretching it, making it grow faster. Alright, let's look at some examples on how this works. Graph each function here. Let's do the square root of x minus 2 plus 5. Well, one thing you should notice is that the minus 2 there is going to tell us that all of our dots from the parent graph are going to go right 2. The plus 5 is going to move all the dots up 5. So if we remind ourselves of the parent graph, the one that we graphed at the very beginning of this video, all of those dots are going to go right 2, up 5. So if I take the dot at 0, 0 currently, and I go right 2, up 5, it's going to land here. Take the dot at 1, 1, go right 2, and up 5, now it lands here. Continue this with all of our dots, you'll get the following shape of the graph. So this is what x squared, the square root of x minus 2 plus 5 would look like. Let's do a few more. Y equals 2 times the square root of x plus 4. And one thing you should know is that 2 is greater than 1, so it's going to stretch by 2. And the plus 4 is going to move all the dots to the left. The best way that I can think of graphing this is you need to ask yourself, what would 2 times the square root of x look like? Okay, to do this, I'm going to show you how this applies with our parent graph. The 2 tells us that we are stretching by a factor of 2, meaning the y values. So if I were to multiply the y value at 0, 0 by 2, it still stays 0. If I were to multiply the y value at 1, 1 by 2, 1 times 2 would bump that ordered pair up to 2. The y value at the next ordered pair is 2 itself. 2 times the 2 that's already out front now bumps it up to a 4. And then the last dot we had at 3. 2 times 3 is 6, so that would jump our dot up to 6, which is about right here. So we have this idea of what the square root, or 2 times the square root of x would look like, but all of those dots that we have drawn there are now going to be moving left 4. So bear with me. So moving that first dot left 4, the second dot left 4, the third dot that we had left 4, and then finally the last one to the left 4. Then we can draw the shape of our graph. This is what 2 times the square root of x plus 4 would look like. Got a few more to look at. How about y equals negative, or the opposite of the square root of x minus 2 plus 2? We've got 3 things taking place here. We've got 1, it's going to reflect over the x-axis, so the graph's going to curve downward to the right. We have the graph going to the right 2, and we have the graph going up 2. So what would negative square root of x look like? Well, we have our parent function, so the opposite of that would reflect all of these dots over the x-axis. So however far the dot is above the x-axis, it's going to be the same distance below. So we would have a dot here, here, this one goes 2 steps below, and the last one would be 3 steps below. Those are all the reflections. Now what I do with all those dots is I move them right 2 and up 2. So our dot then will go right 2, up 2 at 0, 0. The dot that we had at 1, negative 1 goes right 2, up 2. And continue out with the rest of our dots. And we have the picture of our graph there. This is what the negative square root of x minus 2 plus 2 would look like. Okay, so the next thing we need to look at is how do you find the domain in the range of the function? Because our domain does not consist of all real numbers like a lot of our functions that we've worked with this year. One that we got to look at first is domain. We are unable to take square roots of numbers that are less than 0. That takes us out of the real numbers and puts us into the complex numbers. So whatever this thing is that's underneath the square root, the radicand, needs to be greater than or equal to 0. If you look at this inequality that we have right now, if we add the h over, our domain is going to be greater than or equal to that h value. The range depends on 2 things. If a, so that amplitude number out in front of the square root, if it's positive, the range will be f of x values are greater than or equal to the vertical movement number, the k. So the number that is on the outside here. If the a happens to be negative, then the range will be less than or equal to that k number. And to do this, we're going to find the domain and the range of all those examples that we've just graphed above. So state the domain and the range of our square root of x minus 2 plus 5. Well, the domain, take the x minus 2, make sure that it is greater than or equal to 0, add the 2 over. The domain here is x is greater than or equal to 2. The range, there is a positive value in front of here. We don't see a negative sign, so the range here would be f of x is greater than or equal to our vertical movement of 5. Why does this work? Well, let's look at our graph visually. If you see here that the x value of our ordered pair is 2 and the y value is 5, and if we were to calculate or just write out all those ordered pairs, you would see that 2 would be the smallest x value of the ordered pairs, and 5 would be the smallest y value of all those ordered pairs. So everything else would have to be greater than of it. Okay, next example. We got 2 times the square root of x plus 4. You'll notice that I added a 0 in here. If you don't see that vertical movement at all, then you need to put that plus 0 in there to help you find that range. So our domain, take whatever's underneath the square root, make sure that it is greater than or equal to 0. Tells us to subtract 4 over. The domain for this function is x is greater than or equal to negative 4. And then the range, we just look out front and make sure, do we have positive or negative? 2 happens to be positive, so our f of x values are going to be greater than or equal to 0. Again, taking a look at the graph, if you look at the lowest point on this graph, we have an ordered pair at negative 4, 0. If you write out all the ordered pairs of all the dots that make up this graph, negative 4 would be the smallest of the x values, and 0 would be the smallest of the y values. And then we have negative square root of x minus 2 plus 2. Sticking with our rule for the domain, anything that's underneath the square root needs to be greater than or equal to 0. We add our 2 over. The domain now is x is greater than or equal to 2. But here, now we have a negative sign out in front, which if you think about the visual picture, the graph is now sloping underneath or going below. So our f of x values are less than or equal to 2. Okay, so looking at our picture, our x value of this ordered pair up here is negative 2, 2. But if you were to write out all those ordered pairs, and I can even go down to this next one here. We got 1, 2, 3, 4, 5, 6, 7, negative 1, it looks like. 7 is greater than negative 2, so that's why our domain stays greater than or equal to. But the negative 1 compared to the 2 there is definitely less than, so that's why our range has to be switched with its inequality sign. And that's really the main things that we're looking at for these square root functions. Is can you use the transformations to graph a square root function, and then can you also look at some characteristics such as the domain and the range from the equation.